Lesson Introduction. Asset management, security architecture resilience, and physical security are crucial concepts that underpin effective cybersecurity operations. Asset management involves identifying, tracking, and safeguarding an organization's assets, ranging from hardware and software to data and intellectual property. By knowing what assets exist, where they are, and their value to the organization, cybersecurity teams can prioritize their efforts to protect the most critical assets from cyber threats. Security architecture resilience refers to the design and implementation of systems and networks in a way that allows them to withstand and recover quickly from disruptions or attacks. This includes redundancy, fail-safe mechanisms, and robust incident response plans. By building resilience into the security architecture, cybersecurity teams ensure that even if a breach occurs, the impact is minimized and normal operations can be restored quickly. Physical security protects personnel, hardware, software, networks, and data from physical actions and events that could cause severe damage or loss to an organization. This includes controls like access badges, CCTV systems, and locks, as well as sensors for intrusion detection. Physical security is a critical aspect of cybersecurity, as a breach in physical security can lead to direct access to systems and data, bypassing other cybersecurity measures. Together, these concepts support cybersecurity operations, help protect against a wide range of problems, and ensure the continuity of operations in the face of disruptive events. Lesson objectives. In this lesson, you will do the following. Review important data backup concepts. Understand asset management practices. Explore high availability and resilience strategies. Review important physical security concepts. Exam objectives covered. 3.4 Explain the importance of resilience and recovery in security architecture. 4.2 Explain the security implications of proper hardware, software, and data asset management. Asset management is a critical component of effective cybersecurity operations. It involves identifying, classifying, and inventorying an organization's IT assets, including hardware, software, data, and personnel. Effective asset management enables organizations to understand their IT infrastructure, monitor for unauthorized activity, and identify potential vulnerabilities. Asset management is essential for ensuring that all devices and systems are appropriately secured, patched, and updated to mitigate the risks of cyberattacks. Additionally, asset management supports incident response activities, enabling security teams to quickly identify and isolate affected assets during a security incident. By integrating asset management into cybersecurity operations, organizations can strengthen their security posture and better protect their valuable assets against cyber threats.
You know, asset management is a pretty big deal and it involves a life cycle. So, we're going to talk about the security implications of proper hardware and software and data asset management. And to tell us about that, we've got Gareth Marchant. Gareth, how you doing, man?
Hey, James, doing great. Glad to be here.
It's good to have you here. Tell us a bit about your work as an owner of Lighthouse, and let's start talking about asset management.
Yeah, you bet. I spend a lot of time helping folks build and develop the programs and do a lot of workforce development in the cybersecurity space in particular. And one of our first conversations that we have when we talk about our program management is an asset inventory. It's not always what people expect. A lot of times, folks think we're going to talk about firewalls and intrusion detection systems and vulnerability scanning and things. But as they say, you can't build defenses unless you know what you're defending, and an asset inventory is a big part of that. Knowing what you have first and then figuring out a plan to protect it.
That way you don't have things lurking in the shadows. I mean, shadow IT is a serious problem, right?
That's it. Exactly. You got to know what's in your environment. You've got to know what hardware you have. You got to know what kind of data you have, where it is. You have to come up with a plan of, appropriate ways to protect it. Sometimes that's just, sort of an ethical approach. A lot of times it's something that's specified in a external regulation or law.
Sure.
But you've got to know what you got and where it is first.
So people talk about supply chain issues, and so proper asset management can help because you're acquiring things via a process, right? That there are rules.
This is a big space that we're talking about now. As far as asset management, bill
Mm.
of materials describes all of the components that are used to build a product. And one of the products that we all use, probably more than anything, is software.
Right.
And so the idea of a software bill of materials describes all of the elements that comprise a piece of software. Although on the surface it just looks like one app, that's usually built of many different components that are drawn from different places and developed by different teams. And having insight into that can help you identify if there are any potential issues there.
And so we can talk about the ownership of the software, but also the data that runs through those systems, the hardware and the software systems,
It's a
right?
good, yeah, that's a good point. The just like anything, it's all layered. There's lots of life cycles and lots of layers in cyber, and understanding how all of these components come together, where they're used. The person that runs that department typically is the one that's responsible for maintaining the security of these things. I mean, they have to recruit the help of others to know what to do, but ultimately they're assigned ownership of these assets, and so it's on them to be sure that they're being used in appropriate ways.
So moving on from the initial inventory, now we're tracking. We're tracking, if not change management, we're taking a look at our existing inventory, enumerating things and updating things. Is that right? To make sure
Yeah,
you're doing it right?
yeah, exactly. Asset management comes down to exactly those things. Once you've identified what you've got and where it is, and understanding how important it is to the way the business runs, then you have to come up with approaches to keep it safe and secure and make sure that all of those things are being handled in that way. And so the idea of classifications come into light, where you identify different assets and realize, gee, this one's a really really big deal for us to run, whereas this one's perhaps less of a big deal. And then generally you have three different sort of classification buckets, and those classifications have lots of protections associated with them. So really, really important and high value assets have lots of protections, and then assets that are less important have fewer controls. But as soon as the owner, does their due diligence to determine what do I have and how important it is, they kind of place it in one of these three buckets. And as soon as it's placed into one of these classification buckets, it immediately identifies exactly how it's to be protected, and there should be no doubt as what the expectations are.
Okay, so eventually, whether it be data or an application or a piece of hardware, it might come to the end of its use, or you have to kind of put it to bed somehow. Or we could talk about disposal and
Yeah.
decommissioning. Tell us a bit about that.
Yeah, so it's our responsibility to make sure all this data is kept safe and secure according to regulations a lot of times that dictate how these things are to be kept safe, and so that extends through its entire life, including when it goes away. So if I have to keep data safe and secure and it has to stay under my control, if that data is stored on, say, a printer or something, like, because a lot of times when you scan important document or any document, but some of them are important, they're actually stored on the printer, and user credentials are stored on the printer a lot of times. And if it's on, if the responsibility is on me to make sure that data is kept safe and secure, then I have to ensure, even when I'm done with that asset, that no one can gain access to that. So I have to have processes around ensuring that anything that may be on that device has been removed, scrubbed,
Mm,
irreversibly replaced, or perhaps permanently damaged,
mm.
to make sure that it doesn't fall into the wrong hands.
Gary, thank you so much for your perspective on the security side of data asset management and the management of applications and hardware. Sure appreciate it, man.
You bet, James. Pleasure as always.
Asset tracking. An asset management process tracks all the organization's critical systems, components, devices, and other objects of value in an inventory. It also involves collecting and analyzing information about these assets so that personnel can make informed changes or work with assets to achieve business goals. There are many software suites and associated hardware solutions available for tracking and managing assets. An asset management database can store as much or as little information as necessary. Typical data would be type, model, serial number, asset ID, location, users, value, and service information. We are focusing on technical assets that require some degree of configuration. An organization also has many assets with no configuration requirement, such as furniture and buildings. Asset assignment/accounting and monitoring/asset tracking. Asset ownership assignment/accounting and classification are essential components of a well-structured asset management process, ensuring that organizations effectively manage and protect their resources while maintaining accountability. Assigning asset ownership involves designating specific individuals or teams within the organization as responsible for particular assets to establish a clear chain of accountability for asset security, maintenance, and ongoing management. Asset classification involves organizing assets based on their value, sensitivity, or criticality to the organization. This enables the consistent and repeatable application of required security controls, effective prioritization for maintenance and updates, and appropriate budget allocation. Both processes need periodic reviews to account for changes in asset value, sensitivity, or relevance to business operations. Monitoring/asset tracking activities include inventory and enumeration tasks, which involve creating and maintaining a comprehensive list of all assets within the organization, such as hardware, software, data, and network equipment. Regularly updating and verifying the asset inventory helps organizations identify and manage their assets effectively, ensuring they have accurate information about each asset's location, owner, and status. This information is vital for license management, patch deployment, and security incident response. Asset monitoring also involves tracking the performance, security, and usage of assets, allowing organizations to detect potential issues, vulnerabilities, or unauthorized access promptly. Proactive asset monitoring helps mitigate risks, optimize resource utilization, and ensure compliance with regulatory requirements. There are several ways to perform asset enumeration, depending on the size and complexity of the organization and the types of assets involved. Manual inventory. In smaller organizations or for specific asset types, manually creating and maintaining an inventory of assets may be feasible. This process involves physically inspecting assets, such as computers, servers, and network devices, and recording relevant information, such as serial numbers, make and model, and location. Network scanning. Network scanning tools such as MAP, Nessus, or OpenVS can automatically discover and enumerate network devices, including servers, switches, routers, and workstations. These tools can identify open ports, services, and sometimes even the operating systems and applications running on the devices. Asset management software. Asset management software solutions, such as LawnSweeper, ManageEngine, or SolarWinds, can automatically discover, track, and catalog various types of assets, including hardware, software, and licenses. These tools often provide a centralized dashboard for managing the asset inventory, monitoring changes, and generating reports. Configuration Management Database, CMDB. A CMDB is a centralized repository of information related to an organization's IT infrastructure, including assets, configurations, and relationships. Tools like ServiceNow or BMC Remedy can help create and maintain a CMDB, providing a holistic view of the organization's assets and interdependencies. Mobile Device Management, MDM, solutions for organizations with a significant number of mobile devices. MDM solutions like Microsoft Intune, VMware Workspace ONE, or Mobile Iron can help enumerate, manage, and secure smartphones, tablets, and other mobile assets. Cloud Asset Discovery. With organizations increasingly adopting cloud services, cloud-native tools such as AWS Config or Azure Resource Graph, or third-party solutions like CloudAware or CloudCheckr can help discover and catalog assets deployed in the cloud. Asset acquisition/procurement. From the perspective of supporting cybersecurity operations, asset acquisition/procurement policies are critical in ensuring organizations maintain a robust security posture. Key considerations include selecting hardware and software solutions with strong security features, such as built-in encryption, secure boot mechanisms, and regular updates or patches. It is crucial to work with reputable vendors and manufacturers that prioritize security and provide ongoing support to address potential vulnerabilities in their products. Additionally, organizations should consider procuring solutions that integrate seamlessly with their existing security infrastructure, such as firewalls, intrusion detection systems, or security information and event management (SIEM) platforms. This facilitates a more cohesive and effective security strategy. Moreover, Organizations should assess the total cost of ownership, TCO, of the assets, considering the initial purchase price along with the ongoing costs of maintenance, updates, and potential security incidents. Prioritizing cybersecurity during the asset acquisition and procurement process helps organizations build a solid foundation for their security operations, reducing the risk of breaches, enhancing compliance with relevant regulations, and ultimately protecting their critical data and systems. Rate your confidence. Asset protection concepts. From the perspective of cybersecurity operations, assets describe the critical resources, information, and infrastructure components that must be protected from potential threats and unauthorized access. The term asset encompasses resources such as hardware devices, software applications, data repositories, network components, and more. Asset protection is critical to maintaining an organization's information system's integrity, confidentiality, and availability. Cybersecurity teams are responsible for identifying and prioritizing these assets based on their sensitivity and the potential impact on the organization's core functions if they're lost, stolen, or breached. Actively safeguarding assets minimizes the potential impacts of security breaches and reduces the likelihood of loss or damage. Asset identification and standard naming conventions. Tangible assets can be identified using a barcode label or radio frequency ID, RFID, tag attached to the device, or simply using an identification number. An RFID tag is a chip programmed with asset data. When in range of a scanner, the chip activates and signals the scanner. The scanner alerts management software to update the device's location. As well as asset tracking, this allows the management software to track the device's location, making theft more difficult. A standard naming convention makes the environment more consistent for hardware assets and for digital assets, such as accounts and virtual machines. The naming strategy should allow administrators to identify the type and function of any particular resource or location at any point in the Configuration Management Database, CMDB, or network directory. Each label should conform to rules for host and DNS names, support, Microsoft.com/90926/naming-conventions-and-active-directory-for-computers-domains-sites- as well as an ID attribute. The location and function of tangible and digital assets can be recorded using attribute tags and fields or DNS name and TXT resource records. Configuration management ensures that each configurable element within an asset inventory has not diverged from its approved configuration. Change control and change management reduce the risk that changes to these components could cause an interruption to the organization's operations. ITIL is a popular documentation framework of good and best practice activities and processes for delivering IT services. Under ITIL, configuration management is implemented using the following elements. Service assets are things, processes, or people that contribute to delivering an IT service. A configuration item, CI, is an asset that requires specific management procedures to be used to deliver the service. Each CI must be labeled, ideally using a standard naming convention. CIs are defined by their attributes and relationships stored in a configuration management database, CMDB. A baseline configuration is a list of settings that an asset, such as a server or application, must adhere to. Security baselines describe the minimum set of security configuration settings a device or software must maintain to be considered adequately protected. A configuration management system, CMS, describes the tools and databases used to collect, store, manage, update, and report information about CIs. A small network might capture this information in spreadsheets and diagrams, whereas a large organization may invest in dedicated applications designed for enterprise environments. Diagrams are the best way to capture the complex relationships between network elements. Diagrams illustrate the use of CIs in business workflows, logical, IP, and physical network topologies, and network rack layouts. Data backups. Backups play an essential role in asset protection by ensuring the availability and integrity of an organization's critical data and systems. By creating copies of important information and storing them securely in separate locations, backups are a safety net in case of hardware failure, data corruption, or cyber attacks such as ransomware. Regularly testing and verifying backup data is crucial to ensuring the reliability of the recovery process. In an enterprise setting, simple backup techniques often prove insufficient to address large organizations' unique challenges and requirements. Scalability becomes a critical concern when vast amounts of data need to be managed efficiently. Simple backup methods may struggle to accommodate growth in data size and complexity. Performance issues caused by simple backup techniques can disrupt business operations because they slow down applications while running and typically have lengthy recovery times. Additionally, enterprises demand greater granularity and customization to target specific applications, databases, or data subsets, which simple techniques often fail to provide. Compliance and security requirements necessitate advanced features such as data encryption, access control, and audit trails that simplistic approaches typically lack. Moreover, robust disaster recovery plans and centralized management are essential components of an enterprise backup strategy. Simple backup techniques might not support advanced features like off-site replication, automated failover, or streamlined management of the diverse systems and geographic locations that comprise a modern organization's information technology environment. Critical capabilities for enterprise backup solutions typically include the following features: support for various environments, virtual, physical, and cloud; data deduplication and compression to optimize storage space; instant recovery and replication for quick failover; ransomware protection and encryption for data security; granular restore options for individual files, folders, or applications; reporting, monitoring, and alerting tools for effective management; integration with popular virtualization platforms, cloud providers, and storage systems. Data deduplication describes a data compression technique that optimizes storage space by identifying and eliminating redundant data. It works by analyzing data blocks within a dataset and comparing them to find identical blocks. Instead of storing multiple copies of the same data, deduplication stores a single copy and creates references or pointers to that copy for all other instances. Deduplication can be performed at different levels, such as file level, block level, or byte level. Deduplication significantly minimizes storage requirements and improves data transfer efficiency, particularly in backup and data replication processes, by reducing the amount of duplicate data stored. Backup frequency. Many dynamics influence data backup frequency requirements, including data volatility, regulatory requirements, system performance, architecture capabilities, and operational needs. Organizations with highly dynamic data or stringent regulatory mandates may opt for more frequent backups to minimize the risk of data loss and ensure compliance. Conversely, businesses with relatively stable data or less stringent regulatory oversight might choose less frequent backups, balancing data protection, data backup costs, and maintenance overhead. Ultimately, the optimal backup frequency is determined by carefully assessing an organization's regulatory requirements, unique needs, risk tolerance, and resources. On-site and off-site backups. The need for on-site and off-site backups must be balanced, as they are crucial in securing critical data and ensuring business continuity. On-site backups involve storing data locally, in the same location as the protected systems, on devices such as hard drives or tapes to provide rapid access and recovery in case of data loss, corruption, or system failures. On the other hand, off-site backups involve transferring data to a remote location to ensure protection against natural disasters, theft, and other physical threats to local infrastructure, as well as catastrophic system loss that can result from ransomware infection, for example. Ransomware poses a significant threat to businesses and organizations by encrypting vital data and demanding a ransom for its release. In many cases, ransomware attacks also target backup infrastructure, hindering recovery efforts and further exacerbating the attack's impact. Perpetrators often employ advanced techniques to infiltrate and compromise both primary and backup systems, rendering them useless when needed. Organizations can implement several strategies to defend against this risk, such as maintaining air-gapped backups physically disconnected from the network, thereby actively preventing ransomware from accessing and encrypting them. Recovery validation. Critical recovery validation techniques play a vital role in ensuring the effectiveness and reliability of backup strategies. Organizations can identify potential issues and weaknesses in their data recovery processes by testing backups and making necessary improvements. One common technique is the full recovery test, which involves restoring an entire system from a backup to a separate environment and verifying the fully functional recovered system. This method helps ensure that all critical components, such as operating systems, applications, and data, can be restored and will function as expected. Another approach is the partial recovery test, where selected files, folders, or databases are restored to validate the integrity and consistency of specific data subsets. Organizations can perform regular backup audits, checking the backup logs, schedules, and configurations to ensure backups are created and maintained as intended and required. Furthermore, simulating disaster recovery scenarios, such as hardware failures or ransomware attacks, provides valuable insights into an organization's preparedness and resilience. Recovery validation strategies are essential because backups can complete with 100% success, but mask issues until the backup set is used for a recovery. Additionally, many organizations are unaware of the time required to perform a recovery, as recovery times are often far longer than assumed. Advanced data protection.
Snapshots.
Snapshots play a vital role in data protection and recovery, capturing the state of a system at a specific point in time. Virtual machine, VM, file system, and storage area network, SAN, snapshots are three different types, each targeting a particular level of the storage hierarchy. VM snapshots, such as those created in VMware vSphere or Microsoft Hyper-V, capture the state of a virtual machine, including its memory, storage, and configuration settings. This allows administrators to roll back the VM to a previous state in case of failures, data corruption, or during software testing. File system snapshots, like those provided by ZFS or BTRFS, capture the state of a file system at a given moment, enabling users to recover accidentally deleted files or restore previous versions of files in case of data corruption. SAN snapshots are taken at the block-level storage layer within a storage area network. Examples include snapshots in NetApp or Dell EMC storage systems, which capture the state of the entire storage volume, allowing for rapid recovery of large datasets and applications. By utilizing VM, file system, and SAN snapshots, organizations can enhance their data protection and recovery strategies, ensuring the availability and integrity of their data across different storage layers and systems. Description. A drop-down on the top left reads, Win10 DOC. The window is divided into two parts. The left part has the head hardware on the top and management at the bottom. The head hardware has subheads: add hardware, firmware, memory, processor, SCSI controller, and network adapter. The head management has subheads: name, integration services, checkpoints selected, smart paging file location, automatic start action, and automatic stop action. The right part is titled checkpoints. The text below reads, you can configure options for checkpoint for this virtual machine. Checkpoint type, checkbox enable checkpoint selected. The text below reads, select the type of checkpoint that will be created when users choose to checkpoint this virtual machine. Production checkpoints radio button is selected. The text below reads, use backup technology in the guest operating system to create data-consistent checkpoints that don't include information about running applications. A checkbox creates standard checkpoints if it's not possible to create a production checkpoint is selected. The text below reads, take a checkpoint with full application state if it is not possible to use backup technology inside the guest operating system. Standard checkpoints radio button is not selected. The text below reads, create application-consistent checkpoints that capture the current state of applications. Below is a section titled Checkpoint File Location. OK, selected. cancel, and apply buttons are on the bottom right. The checkpoint configuration section for a Hyper-V virtual machine. Checkpoints refer to Microsoft's implementation of snapshot functionality. Screenshot used with permission from Microsoft. Replication and journaling. Replication and journaling are data protection methods that ensure data availability and integrity by maintaining multiple copies and tracking changes to data. Replication involves creating and maintaining exact copies of data on different storage systems or locations. Organizations can safeguard against data loss due to hardware failures, human errors, or malicious attacks by having redundant copies of the data. In the event of a failure, the replicated data can be utilized to restore the system to its original state. A practical example of replication is database mirroring, where an organization maintains primary and secondary mirrored databases. Any changes made to the primary database are automatically replicated to the secondary database, ensuring data consistency and availability if the primary database encounters any issues. On the other hand, journaling records changes to data in a separate, dedicated log known as a journal. Organizations can track and monitor data modifications and revert to previous states if necessary. Journaling is beneficial for data recovery in system crashes. It enables the system to identify and undo any incomplete transactions that might have caused inconsistencies, or replay transactions that occurred after the full system backup was completed. This provides greater granularity for restores and greatly minimizes data loss. A practical example of journaling is using file system journaling, such as the Journaled File System, JFS, or the New Technology File System, NTFS, with journaling enabled. These file systems maintain a record of all changes made to files, allowing for data recovery and consistency checks after unexpected system shutdowns or crashes. Remote journaling, SAN replication, and VM replication are advanced data protection methods that maintain data availability and integrity across multiple locations and systems. Remote journaling creates and maintains a journal of data changes at a separate, remote location, allowing for data recovery and ensuring business continuity in case of local failures, natural disasters, or malicious attacks. SAN replication duplicates data from one SAN to another in real time or near real time, providing redundancy and protection against hardware failures, human errors, or data corruption. This technique involves synchronous replication, which guarantees data consistency, and asynchronous replication, which is more cost-effective but slightly less stringent in consistency. Meanwhile, VM replication creates and maintains an up-to-date copy of a virtual machine on a separate host or location, ensuring that a secondary VM can quickly take over the workload in the event of a primary VM failure or corruption. By implementing these methods, organizations can bolster their data protection strategies, safeguarding against various risks and ensuring the availability and integrity of their critical data and systems. Encrypting backups. Encryption of backups is essential for various reasons, primarily data security, privacy, and compliance. By encrypting backups, organizations add an extra layer of protection against unauthorized access or theft, ensuring that sensitive data remains unreadable without the appropriate decryption key. This is particularly crucial for businesses dealing with sensitive customer data, intellectual property, or trade secrets, as unauthorized access can lead to severe reputational damage, financial loss, or legal consequences. Copies of sensitive data stored in backup sets are often overlooked. So many industries and jurisdictions have regulations that mandate the protection of sensitive data stored in backups. Encrypting backups helps organizations meet these regulatory requirements and avoid fines, penalties, or legal actions resulting from noncompliance. Secure data destruction. Several common circumstances may necessitate data destruction within an organization to ensure security, compliance, and proper management of resources. At the end of a data retention period, organizations must destroy data in accordance with internal policies and external regulations while optimizing storage resources. Legal and regulatory compliance, such as adhering to the General Data Protection Regulation, GDPR, or the Health Insurance Portability and Accountability Act, HIPAA, also requires the deletion or destruction of specific data when it is no longer needed or if requested by the data subject. Periodically destroying obsolete or outdated data can help maintain efficient storage utilization and reduce the risk of data breaches. Additionally, when decommissioning storage devices or systems, ensure that any stored data is destroyed before disposal or repurposing to prevent unauthorized access to sensitive information. It is critical to use methods appropriate for the type of storage media being decommissioned. For hard disk drives, HDDs, data wiping methods such as overwriting with zeros or multiple patterns can be effective. This process can include a single pass of zeros or more complex patterns involving multiple passes to thwart attempts at data recovery. For solid-state drives, SSDs, traditional overwriting methods are less effective due to wear leveling and bad block management. Instead, use commands such as the ATA Secure Erase, which are designed to handle the specific challenges of SSD technology by instructing the drive's firmware to internally sanitize all stored data, including that within inaccessible marked as bad memory cells. Asset disposal. Asset disposal/decommissioning concepts focus on the secure and compliant handling of data and storage devices at the end of their life cycle, or when they are no longer needed. Some important concepts include the following. Sanitization refers to the process of removing sensitive information from storage media to prevent unauthorized access or data breaches. This process uses specialized techniques such as data wiping, degaussing, or encryption to ensure that the data becomes irretrievable. Sanitization is particularly important when repurposing or donating storage devices, as it helps protect the organization's sensitive information and maintains compliance with data protection regulations. Destruction involves the physical or electronic elimination of information stored on media, rendering it inaccessible and irrecoverable. Physical destruction methods include shredding, crushing, or incinerating storage devices, while electronic destruction involves overwriting data multiple times or using degaussing techniques to eliminate magnetic fields on storage media. Destruction is a crucial step in the decommissioning process and ensures that sensitive data cannot be retrieved or misused after the disposal of storage devices. Certification refers to the documentation and verification of the data sanitization or destruction process. This often involves obtaining a certificate of destruction or sanitization from a reputable third-party provider, attesting that the data has been securely removed or destroyed in accordance with industry standards and regulations. Certification helps organizations maintain compliance with data protection requirements, provides evidence of due diligence, and reduces the risk of legal liabilities. Certifying data destruction without third-party involvement can be challenging, as the latter provides an impartial evaluation.
Description.
The active kill disk window shows physical drive information at the top and output at the bottom. The erase disk window shows erase disk option at the top with physical drives below. Two radio buttons named Select All Volumes and Select All Unallocated Space are present. Disk Erase option is selected from the left pane. The right pane shows the following settings. Erase method is set to 1 pass zeros, 1 pass. For buttons, Restore settings show Advanced, Start, Selected, and Cancel are at the bottom. Active kill disk data, wiping software. Screenshot used with permission from Lsoft Technologies, Incorporated. Files deleted from a magnetic type hard disk are not fully erased. Instead, the sectors containing the data are marked as available for writing, and the data they contain are only removed as new files are added. Similarly, the standard Windows Format tool will only remove references to files and mark all sectors as usable. For this reason, the standard method of sanitizing an HDD is called overwriting. This can be performed using the drive's firmware tools or a utility program. The most basic type of overwriting is called zero filling, which sets each bit to 0. Single-pass zero filling can leave patterns that can be read with specialist tools. A more secure method is to overwrite the content with 1 pass of all zeros, then a pass of all ones, and then a third pass in a pseudo-random pattern. Some federal agencies require more than 3 passes. Overwriting can take considerable time, depending on the number of passes required.
Topic 7b.
Redundancy strategies. Exam objectives covered. 1.2 Summarize fundamental security concepts. 3.4 Explain the importance of resilience and recovery in security architecture. Redundancy strategies are essential to an organization's disaster recovery and business continuity planning. These strategies include continuity of operations planning, COOP, which involves developing processes and procedures to ensure critical business functions can continue during and after a disruption. High availability, HA, clustering uses redundant systems that can automatically take over operations in case of a failure, minimizing downtime. Power redundancy ensures critical infrastructure, such as data centers, has backup power sources to continue operations during an outage. Vendor diversity and defense in depth involve using multiple vendors and layers of security to reduce the risk of single points of failure and enhance overall redundancy. Regular testing, including tabletop exercises, failover tests, and simulations, is essential to identify vulnerabilities, evaluate response plans, and improve redundancy measures. By incorporating redundancy strategies, organizations can reduce risks, minimize downtime, and ensure the continuity of their critical business functions. Rate Continuity of operations. Continuity of operations, COOP, refers to the process of ensuring that an organization can maintain or quickly resume its critical functions in the event of a disruption, disaster, or crisis. COOP concepts and strategies aim to minimize downtime, protect essential resources, and maintain business resilience. Key elements of a COOP plan include identifying critical business functions, establishing priorities, and determining the resources needed to support these functions. Strategies often involve creating redundancy for IT systems and data, such as implementing off-site backups, failover systems, and disaster recovery solutions. Additionally, organizations may consider alternative work arrangements, such as remote work or co-location arrangements, to maintain operations during a crisis. Developing clear communication and decision-making protocols ensures that employees understand their roles and responsibilities during an emergency. Regular testing and updating of continuity of operations plans, COOP, are crucial to ensure the organization can maintain essential functions during and after disruptive events. Realistic scenarios designed to simulate various disruptions, such as natural disasters, cyber attacks, or pandemics, must be used to assess the plan's effectiveness. Testing methods often include tabletop exercises, isolated functional tests, or full-scale drills. Each approach provides different levels of assurance and must therefore use pre-established evaluation criteria for measuring performance. In essence, COOP strategies focus on proactively preparing for disruptions, ensuring that organizations can continue to deliver essential services and minimize the impact of unforeseen events on their operations. Backups. Backups play a critical role in the continuity of operations plans, COOP, by safeguarding against data loss and restoring systems and data in the event of disruptions. Regular testing verifies the integrity and effectiveness of backups. Testing backups helps ensure the backup process functions correctly by simulating various scenarios and allows organizations to identify any issues or gaps in the backup and recovery process. Testing backups validates the recoverability of critical systems and data, reducing the risk of data loss and minimizing downtime associated with disruptive events. Additionally, testing backups allows organizations to assess their recovery plans, evaluate the speed and efficiency of their backup systems, and ensure compliance with regulatory requirements. Inadequate backup processes can lead to extended downtime, critical data loss, financial losses, reputation damage, and noncompliance. Relationship to business continuity. Continuity of operations, COOP, and business continuity, BC, are closely related concepts that both focus on maintaining the ongoing functioning of an organization during and after disruption, disaster, or crisis. However, they differ slightly in terms of their scope and primary objectives. Continuity of operations primarily addresses the continuity of critical functions and services within an organization during an emergency or disaster. It often involves the development and implementation of strategies to maintain or restore essential operations, such as redundant IT systems, offsite backups, and disaster recovery solutions. COOP usually encompasses a shorter time frame, focusing on the immediate response to a disruption and the steps taken to resume critical functions as quickly as possible. Business continuity, on the other hand, takes a broader approach, considering not only the continuity of critical functions, but also the overall resilience and recovery of the entire organization. Business continuity planning includes the assessment of risks, the development of strategies to mitigate those risks, and the creation of plans to maintain or restore business operations in the face of various threats. This may involve addressing supply chain management, employee safety and communication, legal and regulatory compliance, and reputation management. Business continuity aims to ensure the long-term viability of an organization following a disruption, encompassing both immediate response and ongoing recovery efforts. Continuity of operations is a component of the broader business continuity concept. Both are focused on maintaining the ongoing functioning of an organization during disruptions, but COOP is primarily concerned with the immediate response and restoration of critical functions, while business continuity encompasses a more comprehensive approach to ensure the overall resilience and recovery of the entire organization. Capacity planning. Capacity planning is a critical process in which organizations assess their current and future resource requirements to ensure they can efficiently meet their business objectives. This process involves evaluating and forecasting the necessary resources in terms of people, technology, and infrastructure to support anticipated growth, changes in demand, or other factors that may impact operations. For people, capacity planning considers the number of employees, their skill sets, and the potential need for additional training or hiring to meet future demands. This may involve evaluating workforce productivity, analyzing staffing levels, and identifying potential skills gaps. In terms of technology, capacity planning encompasses the assessment of hardware, software, and network resources required to support business operations, taking into account factors such as performance, scalability, and reliability. Organizations must ensure they have the right technology resources in place to handle increasing workloads and support new applications or services. When it comes to infrastructure, capacity planning involves evaluating physical facilities, such as data centers and office spaces, to determine whether they can accommodate projected growth and maintain business continuity. This may include considerations for power, cooling, and connectivity, as well as planning for potential expansion or relocation. Organizations use various capacity planning methods, including trend analysis, simulation modeling, and benchmarking, to help forecast their needs. Trend analysis examines historical data to identify patterns and trends in resource usage, demand, and performance. Organizations can forecast future resource requirements by understanding past patterns. This type of analysis can help identify potential bottlenecks or other areas that require attention. Simulation modeling leverages computer-based models to simulate real-world scenarios. Organizations can assess the impact of changes in demand, different resource allocation strategies, or system configurations to make informed decisions and optimize resource allocation to meet anticipated needs. Benchmarking requires a comparison of an organization's performance metrics against industry standards or best practices. Benchmarking provides a comparatively simple way to identify areas for improvement and establish performance targets. Ultimately, effective capacity planning allows organizations to optimize resource allocation, reduce costs, and minimize the risk of downtime or performance issues, ensuring they can continue to meet their business goals and maintain a competitive edge. Capacity planning risks. People risks associated with capacity planning. People risks associated with capacity planning may include insufficient staffing or skills gaps, leading to inadequate resource allocation or ineffective utilization. Lack of cross-training or succession planning can create dependency on specific individuals, increasing vulnerability to disruptions. Additionally, resistance to change, lack of employee engagement, or ineffective communication can hinder successful security operations. Cross-training, requires employees to develop skills and knowledge outside their primary roles to mitigate the risk of relying heavily on specific individuals or teams. By cross-training employees, organizations can ensure that multiple individuals can perform critical tasks, reducing the dependence on a single employee or team. Cross-training promotes flexibility, resilience, and continuity within the workforce. Remote work plans outline strategies for employees to work effectively outside the traditional office environment. Remote work plans define communication channels, technology requirements, and expectations for remote work arrangements. Established remote work plans allow organizations to seamlessly transition to remote operations, ensuring business continuity and minimizing the impact of disruptions. Alternative reporting structures describe backup or temporary reporting relationships to reduce the risk associated with single points of failure in management or decision-making. Organizations can maintain operations and decision-making even if key personnel are unavailable by identifying interim individuals or teams. Effective communication is paramount in reducing risk during disruptive events. Clear and timely communication channels ensure that employees, stakeholders, and customers receive accurate information, instructions, and updates. Clear communication helps manage expectations, reduce confusion, and facilitate coordinated responses. Communication fosters trust, promotes employee engagement, and ensures everyone is aligned with the organization's response plans. Additionally, communication plays a vital role in disseminating information about alternative work arrangements, changes in reporting structures, and other critical updates during a disruptive event. Technologies and software associated with remote work. Virtual Private Network, VPN, provides secure access to an organization's internal network and resources. Remote desktop software allows remote access to computers or virtual desktops in the office or the tools used by the help desk and service center teams to support employees. Cloud-based tools, platforms like Microsoft 365, Google Workspace, Dropbox, Slack, and many other popular tools enable remote team collaboration, document sharing, and communication. Video conferencing software, applications like Zoom, Microsoft Teams, or WebEx facilitate virtual meetings, conference calls, and screen sharing. Instant messaging and chat tools, applications like Slack, Microsoft Teams, or Discord enable real-time communication and quick collaboration. Virtual phone systems. Cloud-based phone systems allow employees to make and receive calls remotely using their computers or mobile devices. Project management tools. Platforms like Trello, Asana, or Jira assist in task management, project tracking, and team coordination. Changes in workforce capacity. Layoffs can introduce a range of cybersecurity and physical risks to an organization, making it crucial to consider these factors within capacity planning efforts. Disgruntled employees may pose a significant cybersecurity risk, potentially engaging in unauthorized access or misuse of sensitive data and systems. Additionally, the loss of experienced employees may result in insufficient knowledge transfer to the remaining staff, leading to security gaps and misconfigurations. Furthermore, improper revocation of access to systems and data for laid-off employees can leave organizations vulnerable. In terms of physical risks, departing employees may resort to theft or sabotage of physical assets or exploit their knowledge of safety protocols and procedures to compromise the organization's security. Unauthorized access to premises is another concern if access credentials are not revoked promptly. Capacity planning is essential in managing these risks. It enables organizations to assess resource requirements and make strategic decisions about staffing levels and resource allocation. By incorporating potential layoffs into capacity planning, organizations can proactively prepare for the associated risks and minimize their impact. Implementing robust offboarding procedures, ensuring proper knowledge transfer, and maintaining a strong security culture among remaining employees are crucial in mitigating risks. In conclusion, considering the potential risks associated with layoffs during capacity planning helps organizations maintain a secure environment and protect their valuable assets. Other risks associated with poor capacity planning. Poor capacity planning regarding technology and infrastructure can have significant consequences for an organization's cybersecurity and physical security. Overloaded systems resulting from inadequate capacity planning can increase susceptibility to crashes, failures, and denial of service (DOS) attacks. Additionally, limited resources may lead to performance degradation, potentially causing organizations to neglect essential security measures and updates. Failing to invest in the right security technologies or maintain the necessary infrastructure to protect against emerging threats leaves organizations more vulnerable to cyber attacks. Physically, poor capacity planning may result in insufficient investment in security measures such as access control systems, surveillance cameras, or secure facilities, exposing organizations to unauthorized access or theft. Overlooking capacity requirements for power and cooling can cause overheating or power failures in data centers, leading to hardware failures, data loss, or downtime. Furthermore, inadequate planning for future growth can limit an organization's ability to scale its operations, potentially affecting its responsiveness to security incidents or implementation of new security measures. In contrast, overestimating capacity needs during capacity planning can negatively impact an organization. Increased costs from unnecessary expenses on technology, infrastructure, and personnel strain budgets and divert funds from other critical areas. Inefficient resource utilization can lead to low utilization rates, which can negatively affect the return on investment, ROI, and overall operational effectiveness. Overestimating capacity needs can contribute to higher energy consumption, driving up costs and increasing the organization's carbon footprint and environmental impact. Deploying more resources than necessary can introduce increased complexity in managing and maintaining technology and infrastructure. This added complexity could create challenges for IT teams, making it more difficult to identify and resolve issues or optimize performance. Additionally, the opportunity cost of investing in excess capacity can be significant, as resources may be diverted from other essential projects or initiatives, potentially hindering innovation or market growth. To avoid these potential problems, organizations must strive for a balanced approach to capacity planning, considering current and future needs while remaining flexible and adaptable to changing circumstances. Regularly reviewing and updating capacity plans, along with employing techniques such as monitoring, forecasting, and resource scaling, can help organizations optimize resource allocation and mitigate the risks associated with overestimating capacity needs. High availability. High availability, HA, is crucial in IT infrastructure, ensuring systems remain operational and accessible with minimal downtime. It involves designing and implementing hardware components, servers, networking, data centers, and physical locations for fault tolerance and redundancy. In a high availability setup, redundant hardware components, such as power supplies, hard drives, and network interfaces, reduce the risk of failure by allowing the system to continue functioning if one component fails. Servers are often deployed in clusters or paired configurations, which allows automatic failover from a primary server to a secondary server in case of an issue. Networking components, including switches, routers, and load balancers, are also designed with redundancy in mind to maintain seamless connectivity. As the backbone of high-availability infrastructure, data centers employ redundant power sources, cooling systems, and backup generators to ensure continuous operation. Additionally, organizations may deploy data centers in geographically diverse locations to mitigate the impact of natural disasters or other large-scale events, further enhancing high availability and disaster recovery capabilities. The concept of availability can be measured over a defined period, such as 1 year. Availability can be measured as an uptime value or percentage. It can also be calculated as the time or percentage that a system is unavailable downtime. The maximum tolerable downtime, MTD, metric expresses the availability requirement for a particular business function. High availability is usually loosely described as 24/7, 24 hours per day, 7 days per week, or 24 by 365, 24 hours per day, 365 days per year. For a critical system, availability is described using the nines term, such as 2 nines, 99%, up to 5 or 6 nines, 99.9999%. The following chart identifies the maximum amount of downtimes each of the nines represent. Nines value: availability, annual downtime, HH, S, 6, 99.9999%, 32 seconds. 5, 99.999%, 5 minutes and 15 seconds. 4, 99.99%, 52 minutes and 34 seconds. 3, 99.9%, 8 hours, 45 minutes and 36 seconds. 2, 99%, 87 hours and 36 minutes. Downtime is calculated from the sum of scheduled service intervals plus unplanned outages over the period. System availability can refer to an overall process, but also to availability at the level of a server or individual component. Scalability and elasticity. High availability also means that a system can cope with rapid growth in demand. These properties are referred to as scalability and elasticity. Scalability is the capacity to increase resources to meet demand within similar cost ratios. This means that if service demand doubles, costs do not more than double. There are two types of scalability. To scale out is to add more resources in parallel with existing resources. To scale up is to increase the power of existing resources. Elasticity refers to the system's ability to handle these changes on demand in real time. A system with high elasticity will not experience a loss of service or performance if demand suddenly increases rapidly. Fault tolerance and redundancy. A system that can experience failures and continue to provide the same or nearly the same level of service is said to be fault tolerant. Fault tolerance is often achieved by provisioning redundancy for critical components and single points of failure. A redundant component is one that is not essential to the normal function of a system, but that allows the system to recover from the failure of another component. Site considerations. Enterprise environments often provision resiliency at the site level. An alternate processing or recovery site is a location that can provide the same or similar level of service. An alternate processing site might always be available and in use, while a recovery site might take longer to set up or only be used in an emergency. Operations are designed to fail over to the new site until the previous site can be brought back online. Failover is a technique that ensures a redundant component, device, application, or site can quickly and efficiently take over the functionality of an asset that has failed. For example, load balancers provide failover in the event that one or more servers or sites behind a load balancer are down or are taking too long to respond. Once the load balancer detects this, it will redirect inbound traffic to an alternate processing server or site. Thus, redundant servers in the load balancer pool ensure there is no or minimal interruption of service. Site resiliency is described as hot, warm, or cold. A hot site can fail over almost immediately. It generally means the site is within the organization's ownership and ready to deploy. For example, a hot site could consist of a building with operational computer equipment kept updated with a live dataset. A warm site could be similar, but with the requirement that the latest dataset needs to be loaded. A cold site takes longer to set up. A cold site may be an empty building with a lease agreement in place to install whatever equipment is required when necessary. Providing redundancy on this scale is generally very complicated and expensive. Another issue is that creating duplicate sites and data also doubles, or more, the complexity of securing the resources. The same security procedures must apply to redundant sites, spare systems, and backup data as applied to the main copy. Geographic dispersion refers to the distribution of recovery sites across different geographic locations for disaster recovery, DR, purposes. The concept aims to ensure that recovery sites are located far enough apart to minimize the impact of regional disasters, such as natural calamities or localized incidents. By strategically dispersing recovery sites, organizations can ensure the resilience of their recovery strategies and reduce the risk of a single catastrophic event affecting all business operations. Cloud as disaster recovery, DR. Several factors drive organizations to use cloud services for data center or site redundancy. Cost efficiency plays a significant role as cloud providers offer more affordable redundancy and backup options due to their economies of scale. Economies of scale is a concept that refers to the cost advantages that businesses can achieve when they increase production and output. Essentially, the more a company produces, the cheaper it becomes to deliver those products. The scalability of cloud services allows businesses to incorporate redundant capabilities without over-provisioning resources. For example, geographic diversity provided by cloud providers helps protect against regional outages or disasters, but incorporating this type of redundancy for a private organization would be cost-prohibitive and unwarranted. Faster deployment of capabilities when using cloud platforms enables organizations to set up and deploy redundant systems quickly, far more rapidly than could be done when building infrastructure from scratch. Simplified management is another critical factor, with cloud providers offering tools and services that reduce the complexity of managing redundant infrastructure. Improved security and compliance are also important considerations, as cloud providers invest heavily in these areas, helping organizations meet data protection and redundancy regulatory requirements. Testing redundancy and high availability. Testing high availability, load balancing, and failover technologies is critical and is designed to assess the ability to remain operational during heavy workloads, component failures, or scheduled maintenance. Load testing incorporates specialized software tools to validate a system's performance under expected or peak loads and identify bottlenecks or scalability issues. Failover testing focuses on validating failover processes to ensure a seamless transition between primary and secondary infrastructure. Testing monitoring systems validate effective detection and response to failures and performance issues. Robust testing practices allow organizations to ensure that high availability, load balancing, and failover technologies effectively fulfill their purpose to minimize unexpected outages and maximize performance. Clustering. Where load balancing distributes traffic between independent processing nodes, clustering allows multiple redundant processing nodes that share data with one another to accept connections. This provides redundancy. If one of the nodes in the cluster stops working, connections can fail over to a working node. To clients, the cluster appears to be a single server. A load balancer distributes client requests across available server nodes in a farm or pool and is generally associated with managing web traffic, whereas clusters are used to provide redundancy and high availability for systems such as databases, file servers, and others. Virtual IP. For example, an organization might want to provision 2 load balancer appliances so that if one fails, the other can still handle client connections. Unlike load balancing with a single appliance, the public IP used to access the service is shared between the 2 instances in the cluster. This arrangement is referred to as a virtual IP or shared or floating address. The instances are configured with a private connection, on which each is identified by its real IP address. This connection runs a redundancy protocol, such as Common Address Redundancy Protocol, CARP, enabling the active node to own the virtual IP and respond to connections. The redundancy protocol also implements a heartbeat mechanism to allow failover to the passive node if the active one should suffer a fault. Description. Left consists of a virtual server, active redundant load balancer, and passive redundant load balancer. The web server farm on the right consists of 3 web servers. The steps are as follows. 1. Load balancing service configured as active or passive cluster. 2. Nodes in the cluster are connected by internal IPs and a redundancy protocol. 3. The active node responds to requests on the virtual IP. Topology of clustered load balancing architecture. Images copyright 123rf.com. Active/passive A/P and active/active A/A clustering. In the previous example, if one node is active, the other is passive. This is referred to as active/passive clustering. The biggest advantage of active/passive configurations is that performance is not adversely affected during failover. However, there are higher hardware and operating system costs because of the unused capacity. An active/active cluster means that both nodes are processing connections concurrently. This allows the administrator to use the maximum capacity from the available hardware while all nodes are functional. In the event of a failover, the workload of the failed node is immediately and transparently shifted onto the remaining node. At this time, the workload on the remaining nodes is higher and performance is degraded. N+1 and N+M configurations. In a standard active/passive configuration, each active node must be matched by a passive node. To reduce the costs associated with passive nodes, N+1 and N+M configurations are used. N+1 configuration. Here, a single passive node is shared among multiple active nodes. For example, with 5 active nodes, instead of having 5 passive nodes, only one passive node is provisioned to take over for any of the active nodes that might fail. This setup significantly reduces the number of passive nodes needed. N+M configuration. In this setup, multiple passive nodes are shared among multiple active nodes. For instance, with 10 active nodes, there might be 2 or 3 passive nodes available. These passive nodes can take over in case of failures, offering a balance between redundancy and cost efficiency. Application clustering. Clustering is also very commonly used to provision fault-tolerant application services. If an application server suffers a fault in the middle of a session, the session state data will be lost. Application clustering allows servers in the cluster to communicate session information to one another. For example, if a user logs in on one instance, the next session can start on another instance, and the new server can access the cookies or other information used to establish the login. Power redundancy. All types of computer systems require a stable power supply to operate. Electrical events, such as voltage spikes or surges, can crash computers and network appliances, while loss of power from undervoltage events or power failures will cause equipment to fail. Power management means deploying systems to ensure that equipment is protected against these events and that network operations can either continue uninterrupted or be recovered quickly. Dual power supplies. An enterprise-class server or appliance enclosure is likely to feature 2 or more power supply units, PSUs, for redundancy. A hot plug PSU can be replaced, in the event of failure, without powering down the system. Managed Power Distribution Units, PDUs. The power circuits supplying grid power to a rack, network closet, or server room must be enough to meet the load capacity of all the installed equipment, plus room for growth. Consequently, circuits to a server room will typically be of higher capacity than domestic or office circuits, 30 or 60 amps as opposed to 13 amps, for instance. These circuits may be run through a power distribution unit, PDU. These come with circuitry to clean the power signal, provide protection against spikes, surges, and undervoltage events, and integrate with uninterruptible power supplies, UPSs. Managed PDUs support remote power monitoring functions, such as reporting load and status, switching power to a socket on and off, or switching sockets on in a particular sequence. Battery backups and uninterruptible power supplies, UPSs. If there is a loss of power, system operation can be sustained for a few minutes or hours, depending on load, using a battery backup. A battery backup can be provisioned at the component level for disk drives and RAID arrays. The battery protects any read or write operations cached at the time of power loss. At the system level, an uninterruptible power supply, UPS, will provide a temporary power source in a complete power loss. This may range from a few minutes for a desktop-rated model to hours for an enterprise system. In its simplest form, a UPS comprises a bank of batteries and their charging circuit plus an inverter to generate AC voltage from the DC voltage supplied by the batteries. The UPS allows sufficient time to fail over to an alternative power source, such as a standby generator. If there is no secondary power source, A UPS will allow the administrator to at least shut down the server or appliance properly. Users can save files, and the OS can complete the proper shutdown routines. Generators. A backup power generator can provide power to the whole building, often for several days. Most generators use diesel, propane, or natural gas as a fuel source. With diesel and propane, the main drawback is safe storage. Diesel also has a shelf life of between 18 months and 2 years. With natural gas, the issue is a reliable gas supply in the event of a natural disaster. Data centers are also investing in renewable power sources such as solar, wind, geothermal, hydrogen fuel cells, and hydro. The ability to use renewable power is a strong factor in determining the best site for new data centers. Large-scale battery solutions, such as Tesla's PowerPack, tesla.com/PowerPack, may provide an alternative to backup power generators. There are also emerging technologies that use all the battery resources of a data center as a microgrid for power storage. https://www scientificamerican.com/article/how-big-batteries-at-data-centers-could-replace-power-plants. A UPS is always required to protect against any interruption to computer services, as a backup generator cannot be brought online fast enough to respond to a power failure. Generator power is typically introduced via transfer switches that can operate either manually or automatically. The UPS must be sized appropriately to handle power requirements during the transfer process. Rate your confidence. Diversity and defense in depth. Platform diversity is a concept in cybersecurity that refers to using multiple technologies, operating systems, and hardware or software components within an organization's infrastructure. By incorporating a variety of platforms, businesses can reduce the risk of a single vulnerability or attack affecting their entire infrastructure. This approach is important for cybersecurity operations, as it helps create a more resilient environment that can better withstand cyber threats. When an organization relies on a single technology or platform, an attacker who discovers a vulnerability can potentially compromise the entire system. However, with platform diversity, even if one component is compromised, other parts of the system remain secure, limiting the potential damage. Furthermore, a diverse technology landscape can make it more challenging for threat actors to navigate, as they must be familiar with multiple platforms and exploit techniques. In this way, platform diversity deters potential attackers and contributes to the overall robustness of an organization's cybersecurity posture. Defense in depth. Defense in depth is a comprehensive cybersecurity strategy that emphasizes the implementation of multiple layers of protection to safeguard an organization's information and infrastructure. This approach is based on the principle that no single security measure can completely protect against all threats. By deploying a variety of defenses at different levels, organizations can create a more resilient security posture that can withstand a wide range of attacks. For example, a defense-in-depth strategy might include perimeter security measures such as firewalls and intrusion detection systems to protect against external threats. Organizations can implement segmentation, secure access controls, and traffic monitoring at the network level to prevent unauthorized access and contain potential breaches. Endpoint security solutions, such as antivirus software and device hardening, help protect individual devices, while regular patch management ensures software vulnerabilities are addressed promptly. Additionally, implementing strong user authentication methods, such as multi-factor authentication, can further secure access to sensitive data and systems. Finally, employee security awareness training and incident response planning are essential components of a defense-in-depth strategy, helping to minimize human error and ensure a rapid response to security incidents. Vendor diversity. Vendor diversity is essential for several reasons, offering benefits not only in terms of cybersecurity, but also in business resilience, innovation, and competition. Cybersecurity, relying on a single vendor for all software and hardware solutions, can create a single point of failure. The entire infrastructure may be at risk if a vulnerability is discovered in that vendor's products. Vendor diversity introduces multiple technologies, reducing the impact of a single vulnerability and making it more difficult for attackers to exploit the entire system. Business resilience. Vendor diversity mitigates the risk associated with vendor lock-in and ensures that an organization's operations are not solely reliant on one vendor's products or services. If a vendor stops doing business, goes bankrupt, or experiences a significant disruption, having alternatives helps maintain business continuity. Innovation. Diverse vendors bring different perspectives, ideas, and technologies. Leveraging solutions from multiple vendors can lead to a more innovative and agile IT infrastructure, better positioning an organization to adapt to emerging trends and technologies. Competition. Vendor diversity promotes healthy competition in the market, which can lead to better pricing, improved product features, and higher quality customer support. By engaging multiple vendors, organizations can encourage continuous improvement and obtain better value for their investments. Customization and flexibility. Different vendors offer unique solutions that cater to specific needs, and having a diverse vendor ecosystem allows organizations to choose the best fit for their requirements. This flexibility can result in a more tailored and effective IT infrastructure. Risk management. Vendor diversity helps spread the risk associated with potential product or service failures, security breaches, and other issues. Organizations can better manage and mitigate risks by not trusting a single solution provider or supplier. Compliance. In some industries, regulations or industry standards may require organizations to maintain vendor diversity to ensure compliance and reduce the risk of supply chain disruptions or security breaches. Other types of controls contribute to defense in depth, such as physical security controls that block physical access to computer equipment and policies designed to define appropriate use and consequences for noncompliance. Multi-cloud strategies. A multi-cloud strategy offers several benefits for both cybersecurity operations and business needs by leveraging the strengths of multiple cloud service providers. This approach enhances cybersecurity by diversifying the risk associated with a single point of failure, as vulnerabilities or breaches in one cloud provider's environment are less likely to compromise the entire infrastructure. Additionally, a multi-cloud strategy can improve security posture by implementing unique security features and services offered by different cloud providers. From a business perspective, a multi-cloud approach promotes vendor independence, reducing the risk of vendor lock-in and ensuring organizations can adapt to changing market conditions or technology trends. This strategy fosters healthy competition among cloud providers, often leading to more favorable pricing and better service offerings. Furthermore, a multi-cloud strategy enables organizations to optimize their IT infrastructure by selecting the most suitable cloud services for specific workloads or applications, enhancing performance and cost efficiency. In a practical example of a multi-cloud strategy, a company operating a large e-commerce platform can distribute workloads across multiple cloud providers to address high availability, data security, performance optimization, and cost efficiency. By hosting the primary application infrastructure on one cloud provider and using another for backup and disaster recovery, the company ensures continuous operation even during outages. Storing sensitive customer data with a cloud provider that offers advanced security features and compliance certifications meets regulatory requirements. To address latency and performance concerns, the company can leverage a cloud provider with a global network of edge locations for content delivery and caching services. Finally, cost-effective storage and processing services can be used by another provider for big data analytics and reporting. This multi-cloud approach enables the e-commerce company to build a more resilient, secure, and efficient IT infrastructure tailored to their specific needs. Deception technologies. Deception and disruption technologies are cybersecurity resilience tools and techniques to increase the cost of attack planning for the threat actor. Honeypots, honeynets, honey files, and honey tokens are all cybersecurity tools used to detect and defend against attacks. Honeypots are decoy systems that mimic real systems and applications. They are designed to allow security teams to monitor attacker activity and gather information about their tactics and tools. Honeynets are a network of interconnected honeypots that simulate an entire network, providing a more extensive and realistic environment for attackers to engage with. Honey files are fake files that appear to contain sensitive information, used to detect attempts to access and steal data. Honey tokens are false credentials, login credentials, or other data types used to distract attackers, trigger alerts, and provide insight into attacker activity. By deploying these tools, organizations can detect and monitor attacks, gather intelligence about attackers and their methods, and proactively defend against future attacks. These tools can also provide an additional layer of defense by diverting attackers' attention away from real systems and applications, reducing the risk of successful attacks. Disruption strategies. Another type of active defense uses disruption strategies. These adopt some of the obfuscation strategies used by malicious actors. The aim is to raise the attack cost and tie up the adversary's resources. Some examples of disruption strategies include the following: using bogus DNS entries to list multiple hosts that do not exist, configuring a web server with multiple decoy directories or dynamically generated pages to slow down scanning, using port triggering or spoofing to return fake telemetry data when a host detects port scanning activity. This will result in multiple ports being falsely reported as open and slow down the scan. Telemetry can refer to any type of measurement or data returned by remote scanning. Similar fake telemetry could be used to report IP addresses as up when they are not, for instance, using a DNS sinkhole to route suspect traffic to a different network, such as a honeynet, where it can be analyzed.
Reconnaissance tools like Nmap can find vulnerable systems on the internet. These tools scan ranges of IP addresses for systems with interesting ports open, such as Telnet, Remote Desktop, SSH, and FTP. Many ethical hackers like to know who's gathering this kind of information, and there's a simple way to record reconnaissance attempts. In order to record these network scans, we need a computer whose sole purpose is to listen for connection attempts on interesting ports, then log the data about each attempt. This kind of system is called a honeypot. It looks appealing and hackable from the outside, but it's actually recording data about every remote user that attempts to connect. Today, we'll look at how to set up an extremely basic honeypot using a tool called Pentbox. Pentbox is available online, but many people upload copies of the original program. When downloading tools, especially hacking tools, you have to be certain of the tool's integrity so you don't download malicious software. I've already downloaded the tool and put it in a folder named Pentbox, so let's open that now. From my Kali Linux machine, I'll open a terminal and navigate to cd Pentbox. I'll list the folder's contents to make sure everything is there. Pentbox is a Ruby script. Since Ruby is already installed on Kali, we just need to run the script. To do that, I'll type pentbox.rb and press enter. Once it's open, we can see a variety of options. Pentbox does a lot of things, but right now we're only interested in the honeypot utility, which is located under Network Tools. First, I'll select number 2, and then we'll select honeypot, number 3. Once we've selected the honeypot utility, we're presented with the option to either use fast or manual configuration. I'm going to select number 1, the fast auto configuration option, since the manual configuration only lets us change which port the tool listens on. It also lets us set the message to return to the requesting machine. As soon as we press enter, we're told that the honeypot has started running on port 80. Let's try connecting to it with Firefox to see what happens. I'll open up Firefox and type localhost in the address bar. We can see that the honeypot returns back a web page that tells us access has been denied. Interestingly, the auto configuration option returns a line with a date and time. This doesn't change. Actually, it represents the time the tool was started. Now that we've connected to the page, let's see what Pentbox says. Okay, it looks like the honeypot utility is telling us quite a bit of information. The first line of each entry shows that there was a connection attempt and tells us what the IP address of the connecting machine was, as well as the connection time. After that, the honeypot utility tells us the header information that was received when the connection was made. This information includes both the web browser that was used and information about the type of operating system that connected. So, there's a really simple overview of a honeypot's function. This is just a taste of what you can accomplish. There are many more robust tools available that can log information about connections on many different ports and protocols simultaneously, which is a goldmine of data that will help you keep your network safe.
Testing resiliency. Method of testing. Testing system resilience and incident response effectiveness are crucial for organizations to recover from disruptions and maintain business continuity. By conducting various tests, organizations can identify potential vulnerabilities, evaluate the efficiency of their recovery strategies, and improve their overall preparedness for real-life incidents. Tabletop exercises involve teams discussing and working through hypothetical scenarios to assess their response plans and decision-making processes. These exercises help identify knowledge, communication, and coordination gaps, ultimately strengthening the organization's incident response capabilities. For example, a tabletop exercise might simulate a ransomware attack to test how well the organization's IT and management teams collaborate to mitigate the threat and restore operations. Failover tests involve intentionally causing the failure of a primary system or component to evaluate the automatic transfer of operations to a secondary, redundant system. These tests ensure backup systems can seamlessly take over during an actual incident, minimizing downtime and data loss. For example, a failover test could involve simulating the failure of a primary database server to verify that a standby server can successfully assume its role and maintain service continuity. Simulations are controlled experiments replicating real-world scenarios, allowing organizations to assess their incident response processes and system resilience under realistic conditions. These tests can reveal potential bottlenecks, inefficiencies, or vulnerabilities that might not be apparent in less complex tests. For instance, a simulation might involve a cyber attack targeting the organization's network infrastructure to evaluate the effectiveness of security measures and the ability to detect, contain, and remediate the threat. Parallel processing tests involve running primary and backup systems simultaneously to validate the functionality and performance of backup systems without disrupting normal operations. These tests help organizations ensure their backup systems can handle the same workload as primary systems during an incident. For example, an organization might run parallel processing tests to verify that a backup data center can manage the same traffic and processing demand as the primary data center in an outage. Failure to perform tests such as tabletop exercises, failover tests, simulations, and parallel processing can expose organizations to significant risks. With these tests, organizations can recognize potential vulnerabilities and weaknesses in their incident response plans and system resilience designs and use the results of tests to improve existing plans. In a real-life disruption or cyber attack, untested systems and response procedures may fail to perform as expected, leading to extended downtime, data loss, and reputational damage. Moreover, unprepared organizations may face increased costs related to incident recovery and mitigation, and potential regulatory penalties for failing to meet industry standards and compliance requirements. Ultimately, failure to implement these tests can leave organizations inadequately prepared for crises, undermining their ability to maintain business continuity and protect valuable assets. Documentation. Business continuity documentation practices cover planning, implementation, and evaluation. Documentation supports the testing process. Documentation includes test plans outlining the objectives, scope, and methods of tests, and the roles and responsibilities of individuals involved. Test scripts, or scenarios, provide step-by-step instructions for performing the tests, and test results identify strengths and weaknesses of the business continuity plan and the technical capabilities supporting it. Documentation is the foundation for clear communication and reporting of activities. It provides a common reference point for those involved in business continuity testing and facilitates effective communication with management, executive teams, and other relevant stakeholders. Third-party assessments and certifications offer an objective and independent evaluation of an organization's testing practices. Third-party assessments and certifications offer objective evaluation, compliance verification, validation of testing effectiveness, industry recognition, and recommendations for continuous improvement. Examples of third-party evaluations include assessments performed in alignment with ISO 22301, PCI DSS, and SOC2.
Topic 7C.
Physical security. Exam objectives covered. 1.2 Summarize fundamental security concepts. Physical security concepts are a critical component of cybersecurity. Physical security measures, such as access control, video surveillance, and environmental controls, help protect an organization's physical assets, including servers, data centers, and other critical infrastructure from unauthorized access, theft, or damage. Effective physical security practices help prevent unauthorized physical access to sensitive data or systems and reduce the risk of insider threats. Organizations must integrate physical security practices into their cybersecurity strategies to provide a layered approach to security and protect against cyber threats that exploit physical vulnerabilities. Rate your confidence. Physical security controls. Physical security is critical to cybersecurity operations because it provides the first line of defense against physical access to an organization's critical assets. Cybersecurity is about securing digital assets and protecting the physical components that house those assets, such as servers, data centers, and other critical infrastructure. Practical examples of physical security measures in cybersecurity operations include access control mechanisms, such as biometric scanners, smart cards, key fobs, and surveillance systems, including video cameras, motion sensors, and alarms. Additionally, backup power, redundant cooling, and fire suppression systems are critical components of physical security in data centers. Physical access controls depend on the same access control fundamentals as technical system security. Authentication creates access lists and identifies mechanisms to allow approved persons through the barriers. Authorization creates barriers around a resource to control access through defined entry and exit points. Accounting records when entry/exit points are used and detects security breaches. Physical security is often implemented by incorporating zones. Each zone is separated by its own barriers. One or more security mechanisms control entry and exit points through the barriers. Progression through each zone should be increasingly restrictive. Site layout, fencing, and lighting. Physical security through environmental design. Physical security through environmental design is an approach to security that uses the built environment to enhance security and prevent crime. This approach designs physical spaces, buildings, and landscapes to promote non-obvious security features. Physical security via environmental design can be used in various settings, such as residential neighborhoods, commercial districts, schools, and public spaces. By incorporating these design principles, organizations can enhance security, deter criminal activity, and promote a sense of safety and well-being among users. Additionally, physical security via environmental design can be a cost-effective way to improve security because it easily incorporates design elements into new or existing structures at a low cost. Barricades and entry/exit points. A barricade is something that prevents access. As with any security system, no barricade is completely effective. A wall may be climbed, or a lock may be picked. The purpose of barricades is to channel people through defined entry and exit points. Each entry point should have an authentication mechanism so that only authorized persons are allowed through. Effective surveillance mechanisms ensure the detection of attempts to penetrate a barricade by other means. Physical sites at risk of a terrorist attack will use barricades such as bollards and security posts to prevent vehicles from speeding toward a building. Fencing. The exterior of a building may be protected by fencing. Security fencing needs to be transparent, so guards can see any attempt to penetrate it, robust so that it is difficult to cut, and secure against climbing, which is generally achieved by making it tall and possibly by using razor wire. Fencing is generally effective, but the drawback is that it gives a building an intimidating appearance. Buildings that are used by companies to welcome customers or the public may use more discreet security methods. Lighting. Security lighting is enormously important in the perception that a building is safe and secure at night. Well-designed lighting helps to make people feel safe, especially in public areas or enclosed spaces, such as parking garages. Security lighting also acts as a deterrent by making intrusion more difficult and surveillance, whether by camera or guard, easier. The lighting design needs to account for overall light levels, the lighting of particular surfaces or areas, allowing cameras to perform facial recognition, for instance, and avoid areas of shadow and glare. Bollards. Bollards are generally short vertical posts made of steel, concrete, or other similarly durable materials and installed at intervals around a perimeter or entrance. Sometimes bollards are non-obvious and appear as sculptures or as building design elements. They can be fixed or retractable, and some models can be raised or lowered remotely. Bollards can serve several purposes, such as protecting pedestrians from vehicular traffic, preventing unauthorized vehicle access, and providing perimeter security for critical infrastructure and facilities. They are often used to secure government buildings, airports, stadiums, store entrances, and other public spaces. By preventing vehicles from entering restricted areas, bollards can help mitigate the risks of vehicular attacks and accidents. Bollards used to protect the entrance of Reading train station in Britain. Image from user Roger Utter, copyright 123rf.com. Existing structures. There may be a few options to adjust the site layout in existing premises. When faced with cost constraints and the need to reuse existing infrastructure, incorporating the following principles can be helpful. Locate secure zones, such as equipment rooms, as deep within the building as possible, avoiding external walls, doors, and windows. Use a demilitarized zone design for the physical space. Position public access areas so that guests do not pass near secure zones. Security mechanisms in public areas should be highly visible to increase deterrence. Use signage and warnings to enforce the idea that security is tightly controlled. Beyond basic no trespassing signs, some homes and offices also display signs from the security companies whose services they are using. These may convince intruders to stay away. Conversely, entry points to secure zones should be discreet. Do not allow an intruder the opportunity to inspect security mechanisms protecting such zones, or even to know where they are. Use industrial camouflage to make buildings and gateways protecting high-value assets unobtrusive or create high-visibility decoy areas to draw out potential threat actors. Try to minimize traffic passing between zones. The flow of people should be in and out rather than across and between. Give high-traffic public areas high visibility to hinder the covert use of gateways, network access ports, and computer equipment, and simplify surveillance. In secure zones, position display screens or input devices away from pathways or windows. Use one-way glass only visible from the inside out, so no one can look in through windows. Rate your confidence. Continue. Gateways and locks. To secure a gateway, it must be fitted with a lock. A secure gateway will normally be self-closing and self-locking rather than dependent on the user to close and lock it. Lock types can be categorized as follows. Physical are conventional locks that prevent the door handle from being operated without using a key. More expensive types offer greater resistance against lock picking. Electronic are locks, rather than a key, that operate by entering a pin on an electronic keypad. This type of lock is also referred to as cipher, combination, or keyless. A smart lock may be opened using a magnetic swipe card or feature a proximity reader to detect the presence of a physical token, such as a wireless key fob or smart card. Generic examples of locks, from left to right: a standard key lock, a deadbolt lock, and an electronic keypad lock. Images from user macrovector copyright 123rf.com. Biometric is a lock integrated with a biometric scanner. Generic examples of a biometric thumbprint scanner lock and a token-based key card lock. Images from user macrovector copyright 123rf.com. Access control vestibule, mantrap. An access control vestibule, also known as a mantrap, is a security measure that regulates entry to a secure area. It involves two doors or gates that interlock and permit only one individual to pass through at a time. The first door opens after the person is granted access via an access control system, such as a card reader or biometric scanner. Once the person enters the vestibule, the first door shuts. The second door opens only when the first door is firmly shut. This guarantees only one person can enter or exit at a time, preventing unauthorized access or tailgating. Access control vestibules are frequently used in high-security settings like data centers, government buildings, and financial institutions to offer an additional layer of physical security control. They effectively deter unauthorized access to secure areas and safeguard sensitive assets against potential physical attacks. Cable locks. Cable locks attach to a secure point on the device chassis. A server chassis might come with both a metal loop and a Kensington security slot. As well as securing the chassis to a rack or a desk, the position of the secure point prevents the chassis from being opened without removing the cable first. Access badges. Access badges are a fundamental component of physical security in larger organizations where control over access to various locations is critical. Plastic cards embedded with magnetic strips, radio frequency identification, RFID, chips, or near-field communication, NFC, technology are issued to authorized individuals, such as employees, contractors, or visitors instead of physical keys. Access badges replace physical keys, but provide access similarly. This is achieved by requiring the badge to be swiped, tapped, or brought into proximity with a reader at the access point, like a door or a turnstile. The reader communicates with the control system to verify the badge's authenticity and the level of access granted to the badge holder. If the system recognizes the badge as valid and authorized for that area, the door unlocks, granting access. It is important to note that implementing this type of access control system requires magnetic door locking mechanisms and access card readers, which depend upon electrical power and network communications at each access point, such as a doorway. A physical access control system, PACS, is a critical component in managing and maintaining security within a facility. It is a system designed to control who can access specific locations within a building or site. The PACS operates through a combination of hardware and software, including access cards or badges, card readers, access control panels, and a centralized control network. The PACS system provides valuable badge access activity logging capabilities. In addition to controlling access badges also serve as a form of identification, displaying pertinent information about the badge holder, such as their name, title, and photograph. This aids in quickly identifying individuals within a facility and verifying that they are in an area appropriate for their role or purpose. Moreover, access badges can provide valuable data for security audits and investigations. Each time a badge is used, a PACS system can log the time, location, and identity associated with the access event. This can be crucial in investigating security breaches, understanding movement patterns, and even planning emergency evacuation strategies. Rate your security guards and cameras. Surveillance is typically a second layer of security designed to improve the resilience of perimeter gateways. Surveillance may be focused on perimeter areas or within security zones. Human security guards, armed or unarmed, can be placed in front of and around a location to protect it. They can monitor critical checkpoints and verify identification, allow or disallow access, and log physical entry events. They also provide a visual deterrent and can apply their knowledge and intuition to potential security breaches. The visible presence of guards is a very effective intrusion detection and deterrence mechanism, but it is correspondingly expensive. It may not be possible to place security guards within certain zones because they cannot be granted the appropriate security clearance. Training and screening of security guards is imperative. Video surveillance is a cheaper means of providing surveillance than maintaining separate guards at each gateway or zone, though it is still not cheap to set up if the infrastructure is not already in place on the premises. It is also quite an effective deterrent. The other big advantage is that movement and access can be recorded. The main drawback compared to the presence of security guards is that response times are longer and security may be compromised if not enough staff are in place to monitor the camera feeds. CCTV installed to monitor a server room. Image by Dario Lopresti, copyright 123rf.com. The cameras in a CCTV network are typically connected to a multiplexer using coaxial cabling. The multiplexer can then display images from the cameras on one or more screens, allow the operator to control camera functions, and record the images to tape or hard drive. Newer camera systems may be linked in an IP network using regular data cabling. Camera systems and robotics can use AI and machine learning to implement smart physical security. TheVerge.com/2018/1/23/169072. Motion recognition occurs when the camera system is configured with gait identification technology. This means the system can generate an alert when anyone within sight of the camera moves in a pattern that does not match a known and authorized individual. Object detection occurs when the camera system can detect changes to the environment, such as a missing server or unknown device connected to a wall port. Drones/UAV. Cameras mounted on drones can cover wider areas than ground-based patrols. zdnet.com/article/best-security-surveillance- Alarm systems and sensors. Alarms play a vital role in physical security by supplementing other security controls. Alarms alert security personnel and building occupants of potential threats or breaches. They are both detective and deterrent controls, notifying of trouble and discouraging unauthorized access and criminal activity. Alarms are often integrated with other physical security controls, such as access control systems, surveillance cameras, or motion sensors, to enhance their effectiveness. The following list describes several common types of alarms. Circuit uses a circuit-based alarm that sounds when the circuit is opened or closed, depending on the type of alarm. For example, this could be a door or window opening, or by a fence being cut. A closed-circuit alarm is more secure because it cannot be defeated by cutting the circuit like an open-circuit alarm. Motion detection uses a motion-based alarm linked to a detector that is triggered by any movement within an area such as a room, defined by the sensitivity and range of the detector. The sensors in these detectors are either microwave radio reflection, similar to radar, or passive infrared, PIR, which detect moving heat sources. Noise detection uses an alarm triggered by sounds picked up by a microphone. Modern AI-backed analysis and identification of specific types of sound can render this type of system less prone to false positives. Proximity uses radio frequency ID, RFID, tags, and readers to track the movement of tagged objects within an area. This allows an alarm system to detect whether someone is trying to remove equipment. Duress uses an alarm triggered manually by staff if they come under threat. There are many ways of implementing this type of alarm, including wireless pendants, concealed sensors or triggers, and DCT handsets or smartphones. Some electronic entry locks can also be programmed with a duress code different from the ordinary access code. This will open the gateway, but also alert security personnel that the lock has been operated under duress. Circuit-based alarms are suited for use at the perimeter.
Doors.
These may register when a gateway is opened without using the lock mechanism properly, or when a gateway is held open for longer than a defined period. Motion detectors are useful for controlling access to spaces not normally used. Duress alarms are useful for exposed staff in public areas. An alarm might simply sound like an alert or be linked to a monitoring system. Many alarms are linked directly to local law enforcement or third-party security companies. A silent alarm alerts security personnel rather than sounding an audible alarm. Sensor types. Sensors are critical in implementing physical security measures, providing proactive detection and alerting capabilities against potential security breaches. These devices can employ various technologies, including infrared, pressure, microwave, and ultrasonic systems, each with unique advantages and suitable applications. Infrared sensors are commonly used in motion detection systems. They detect changes in heat patterns caused by moving objects, such as a human intruder. These are often used in residential and commercial security systems, triggering alarms or activating security lights when detecting motion. Pressure sensors are typically installed inside floors or mats and are activated by weight. They can be used in high-security areas to detect unauthorized access, or even in retail environments to count foot traffic. Microwave sensors emit microwave pulses and measure the reflection off a moving object. They are often combined with infrared detectors in dual technology motion sensors. These sensors are less likely to trigger false alarms, as the infrared and microwave sensors must be tripped simultaneously to trigger an alarm. These can be useful in securing large outdoor areas like parking lots or fenced areas. Ultrasonic sensors emit sound waves at frequencies above the range of human hearing and measure the time it takes for the waves to return after hitting an object. They are often used in automated lighting systems to switch lights on when someone enters a room and switch them off again when the room is empty. Rate your Lesson 7. Summary. You should be able to explain the importance of asset management, resiliency concepts, and physical security controls in support of cybersecurity operations. Guidelines for asset management and resiliency controls. The following are important asset management concepts. Perform asset identification. Catalog all assets, both physical and intangible, owned by an organization. Include key information such as asset type, location, value, and ownership. Implement asset lifecycle management. This includes rules for procurement, maintenance, depreciation, and eventual retirement or replacement of an asset. Perform asset tracking. Keep track of the location and status of assets, especially those that are mobile or prone to theft. Understand regulatory compliance requirements. Certain assets, such as those related to health and safety, data protection, or environmental impact, must be managed in compliance with specific regulations to avoid legal penalties. Perform disaster recovery and business continuity planning. Plans should be in place to quickly replace or restore critical assets in case of disasters. Secure asset disposal. Using legally compliant and secure methods to destroy data. Ensure adequate capacity planning for people, technology, and infrastructure. Implement high availability strategies, including the following: scalability and elasticity, fault tolerance and redundancy, clustering, site resiliency. Using risk assessments, identify assets that have high availability requirements and provision redundancy to meet this requirement. Hot, warm, or cold site resources to recover from disasters. Use dual power supply, PDUs, PSUs, and generators to make the power system resilient. Use NIC teaming, multiple paths, and load balancing to make networks resilient. Use RAID and multipath I/O to make storage resilient. Implement diversity in technologies and controls. Perform comprehensive testing of resiliency capabilities. Follow these guidelines for deploying or upgrading physical security controls. If possible, design sites as zones to maximize access controls and surveillance for the most secure areas, using industrial camouflage, perimeter network, air gaps, vaults, and safes where applicable. Secure the site perimeter and access points using fencing, barricades/bollards and locks, physical, electronic, and biometric. If using smart cards, use a type that is resistant to cloning/skimming. Monitor the site using security guards, CCTV, and drones/UAV, and use effective lighting to maximize surveillance. Deploy an alarm system, circuit, motion-based, proximity, and/or duress to detect intrusion. Use ID badges to authorize access.